Rabbit here again. So moving on with Rust. So in this video I'll take a overview of the general types used in Rust. So let's get started. So to be able to go through the different types, what I did is I actually created a Rust program, and then I'm going to actually upload it to my GitHub page totally for free, so you can download it. The idea is that I'll go through it generally here, and then if you're sufficiently interested, then you can go get this package, and then you can like copy paste from this program into your own program the templates for the different types. So anyway, let's get started. So the lower level types are so-called machine types, and they're defined as in different sizes. So here you have the 8-bit sizes, and it's always the same naming convention. So when it's unsigned, then it's U, and then you have the 8, which designates the size. And then you have I, which is that it's the signed version of the type. And then I've also printed out, made it so that you can print out the minimum and maximum size. And then you have the 8-bit size variable, and then you have a 16-bit, and it's signed and unsigned. And then you have a 32-bit version, and then you have a 64-bit version. These are all integer types. And then you have two floating point variants. You have a 32-bit version and a 64-bit floating point. Now here we have the printout for the difference. So if you have the 8-bit version, then you see the maximum minimum value. And this is the unsigned, and this is the signed quantity. And then the number gets bigger and bigger and bigger, and then then you get to the 64-bit. It's quite a large integer number. And then when you get into floating points, then you have the 32-bit floating point, and then the 64-bit. Yeah, I know you could have formatted to be more logical, but I thought it's kind of impressive to see all the zeros. So it kind of puts in your mind that that can represent a very large number. So anyway, moving on, and then Rust has this concept of U size and I size, with the same idea. This is the unsigned version, that's the signed version. But this is the size of this will be based on the machine you're running on. So it's equivalent to the machine, the size of a word on your machine. So it will vary. So if you would like to actually wrap around, so loop around. So if you take the minimum or maximum, let's say they take the maximum size, and then you add 1, then it will crash. But if you use this wrapping sub, then adding 1 to the max will actually just wrap it around. So here I just made an example. So in this case I'm just doing a subtract, a wrapping subtract, so that it knows that you actually have to tell Rust explicitly that you want it to wrap around, otherwise it won't do it. Then we have in Rust that you can actually take the type and you can assign it to a constant number. So in this case we have the number 32, and I've designated that it's I size. And then the same here with minus 32, that's an I size. And then you can do calculations, and then you get the answer back. You have the option to print out the numbers. So if they're integer values, then you can designate the output as hexadecimal, octal, or binary literal. So here I've actually included the examples. So here And then here you can also see how do you actually assign a type to a specific constant. So here it uses hexadecimal, and it says that it's a value FF, and that's of type isize. It's the same octal and then binary also. Rust also has a little bit of an odd thing that doesn't exist in other languages that I've seen, that you can actually use the underscore to clarify the number. So you can say, 123,456, and you can actually put an underscore there, and then also you can use an underscore actually between the constant number and the type that you're assigning to. I think this would be very useful if you were dealing with binary numbers, because then you can actually separate the intersections of 8 or 4 or whatever you feel comfortable with. Here we can also handle byte literals. So basically this is converting ASCII into a number with different escape options for the different special characters. Backslash and carriage return and new line and stuff. Tab also. And here we do, you can actually use hexadecimal values also to assign a byte literal. You can also convert integer types by using the as keyword here. So for example, here I said 23 and its type U8, but then I want to convert it to an I16 and assign it to an I16. So then you use this as keyword. So there isn't like this explicit typecasting, so you actually use this syntax instead. Truncating, that's actually a useful feature, especially if you're dealing with hexadecimal binary numbers. So very often you do this. So we say this is a U32, and then you want to actually cut it and get a 16-bit value back. So then you can use the 32-bit value and then just define it as U16, and then you get the lower part. Now in this presentation I'm not going to go through every single method that exists in all different contexts, because there's documentation for that, and nobody would stick around for a presentation like that just listing off the different functions. But I'm going to point out some more generally useful ones, and then show, like in this case, that when you have a type like 2, it's a U8, and then you can actually add the functionality. So you say dot power to the 2, and then here's a special case that if you have a minus here for the number and you want to perform a operation on it, then you need to actually put these brackets around the whole number definition, including the minus sign. If you don't do that, then it will it'll actually do the absolute on the number 2 and not including the minus sign. Yeah, so I actually made it here, and the example where it actually doesn't work, which is maybe not so intuitive. Now I could actually take a little break here and discuss the method that Rust uses that Rust uses inference. So it tries to like understand what the type is. So if it isn't explicitly defined, then it'll try and decide what the type should be. So here I actually added 2 examples. It's in the same source file. So you have build vector where you've gone crazy and you actually explicitly define the type of everything that's used to, you know, the return parameter, the vector type, and, you know, the vector that's being assigned. That's kind of where you do the new, and then, you know, you define the type of the constants, and so everything is. Darn, I missed one. I should have added the type to this, to the V also. No, but that would cause a compile because it's the vectors. And then alternative, you can have like a lightweight, sloppier way of doing it. So then you basically because with this specific function, the only thing you need to define is basically you define the type of the return value, and then basically it can infer the type of everything else that's needed automatically. So where this can get very confusing from time to time as a programmer with Rust is the Rust, as I said, it has its own internal rules for inference of types, and then it's basically a type strict language. Ultimately, so you can get into bottlenecks and stuff where it's converting numbers into a type that you didn't expect, and then the compiler compile time will complain about it. And I just threw in some examples here, you know, like odd one, like this number here. What's it going to be inferred as? Is it a F32 or F64? You know, 2 dot. Is that a unsigned integer, an integer, or is it a floating type? And then, you know, like this one, 1000. You know, you know, what it could fit into a unsigned or a signed 16 or larger. So which one is it going to pick? Will not compile. So yeah, here we put an example here. Yeah, because this was a tricky one I found as an example that it will say that the square root function doesn't exist in this context, and the reasoning is that it doesn't know what specific floating point type 2.0 represents in this specific formatted example. So so it infers the type float, which is like the generic type, and that generic type hasn't got a method square root, because it can't take a square root on a float, because it doesn't know if it's a float 32 or 64. Yeah. Just to highlight these kind of things that may pop up when you're dealing with Rust, so that you're if you read through this, then you're aware of the cases and you won't like freak out that, oh, why doesn't this work? There are a few methods that I found where you can actually find out what the type is. The debug macro on a variable. But then I found out that this might be dependent on the Rust version being used. So theoretically it should, in some versions of Rust, it actually prints out the value, and then it actually suffixes it with the type. But it doesn't seem to do that in all versions of Rust. All the Rust compiler. But this will work. As far as I've tested, it seems to work in most cases. Yeah, and then the type inference for this odd one turned out to be F64, because F64 is the default float type. And then we have a Boolean type. And then Boolean as integer, so you can actually convert a boolean to an I32 or some other integer, assigned integer. So I did the the both examples just so, and then but then the thing is, you want to convert a boolean in the opposite direction, then there's no explicit cast, so then you actually need to program it. So that's the difference with other languages, which is actually kind of can be considered a good feature, because in different programming languages the numeric value of true and false varies very much. And then the other concept being is what can you use as a boolean can actually surprise you. It doesn't actually have to be explicitly a boolean type that can be used as a boolean. Yeah. So Rust is a little bit more tougher on you when it comes to boolean. If you're going to use a boolean type, it has to be a boolean type or a boolean result, very clearly a boolean result, or otherwise you're out of luck. And then, as I said, there's this restriction that using this as you can convert a boolean into a number, but not the other way around. So then we're getting into character representation, and in Rust the type char represents a single Unicode character as a 32-bit value. And then what's tricky with Unicode is that not all the numerical values in that 32-bit number are valid, because their Unicode divides them into sequences of valid areas in the number value field. So like I wrote here, only values from the specific ranges are permitted. And then conversion to integer types is done by using the as keyword. You can only convert directly from type UA, unsigned 8-bit. However, better to use. Then I gave this function here that if you want to actually do conversions. Strings. Yeah, the type is used under different contexts here and there. The string is a sequence of UTF-8 bytes, not chars. And the thing is that when you're talking about UTF-8, then it can be that one character can be represented with multiple bytes. So that's when you look at the memory representation, raw memory representation, it can get confusing real fast. And then here I was into this that there's no point in going into all the sub functionality is available. So I just did a few highlights here. So there's lots of sub functionality of char and string. So like you have the method, is it alphabetic, 2-digit, or len UTF-8, but I say let's look at the documentation if you want to find out details. And then we come to tuples, and this is a common delimited list of different types. It can be initialized using pattern matching. No index-based base access is possible. Be based. Proofreading at the same time I'm doing the video. This is really cool here. Extra comma is permitted and common but not mandatory. And then you can't dynamically add or remove elements if it's a tuple. So here I made some examples here. So you have let first and second assign these two values. And here you see this where you can actually just put in this extra comma. So this is some when the Rust team thought, don't really know why. There are some things in Rust that one just one wonders, like, why? But it's a feature and it works. And I decided to include it in this presentation because you will see this in various Rust source code files, that this is being used consistently. Access via hard-coded member location. So here we created this underscore tuple and it's first and second, and then you can actually access them, the individual ones, by saying, okay, that's the first number and that's the second. It's a hard code, so you do it in the source. So this is not anything that you can't turn it into an index and run it dynamically in a for next loop, right? There's also a variant of a tuple that's relatively common, and it's the empty tuple. And it's often used in the context of the return statement or return object, where you can actually have a list of things that it might return. So it'll return this empty tuple, or it'll return, for example, a standard IO error. You'll see this in lots of places, a similar type of concept. As a return value example, yeah, exactly. So here's a text. So 1, 2, 3, 4, 5, and then you execute a split on it, and it splits it into two numbers, and then you can just put the tuple here, and then you have variables here that will then get those numbers. And then here you can print them out either this way, or you use the two. I put it verbosely here, so you actually get the idea. So you put the whole tuple here, and then you say the first number, and then the second. It actually doesn't have to be numbers, because it can be different data. And we get into pointer type references. So here it's that one and sign reference to a value, or that one value of whatever value it points to. So here we create a string, and then this is an address to the string. And then I did some different printouts, so you can actually see, like, okay, this is the direct string, this is the address of the string, this is a string reference, and then what doesn't work, and then yeah. So just to remind you, okay, how does this work? And then boxes, it's a type where you can allocate the value on the heap. And here we have the example. We have a tuple, 12 eggs, and then we say a new box with the actual tuple in it. I was wondering if I would include raw pointers or unsafe code example here, but I thought I'll include one so that you will recognize this code, or this type of code, when you're working with looking at source code from others. But basically you should avoid using raw pointers because it's basically inherently unsafe. Now the good thing with Rust is that it won't allow you to use unsafe features if you don't specifically tell Rust to do it, which is actually a nice feature. What was this example? Oh, this is a hello world. So we build a hello world string. We get a raw pointer to it, and then we go into unsafe mode. So there's a block called unsafe, and inside that block you're allowed to do horrible things. So in here we just I think it was we replace a character, and then you come out of the unsafe mode, and then you continue with safe Rust. So basically, like, using a pointer is, as long as you're not writing to it, it's not usually considered that dangerous. Yeah, no, it's just using the raw pointer to print out, but you can run this also. So, and then we have an array, and these has a fixed length and can only contain one type. So here we see a setup of an array. So these are, and then you see this weird semicolon syntax for. So then you define the type and then how many of the elements do you have, and then you can initialize it here. And then of course you can get the you can get the length of the array, and then you can print out the array. Here you can sort it, and the thing is, this sorting starts getting into this concept of slices that we'll be covering a little bit later. So, and then we have a vector concept as a dynamic lengthener, and only contain one type. Additional removal of elements is possible. Can live on the heap, so can be large. So then you have this vector macro definition, so you can say v is vector, and then it's this list of numbers or other things. And then here we have a iterative process. I kept this fold example. So it can take the vector and it can iterate it on it, and then it can do the folding on it. So I tried to make it as so it's like taking the two first ones and then doing the multiplication, and then it goes and takes the result and then the next one. So, I tried to make it as, but this is a kind of an idea. The idea with this example was that you can iterate over the vectors and do all kinds of neat tricks. And then you can push stuff onto the vector. You can insert into a specific location. You can remove specific entities. You can pop it off the end. So normal, kind of normal stuff. And then you have this option where you can actually create a vector with an initial initialization. So here you can fill it with 10 minus 1s. And then the thing is that this vector, this here, it's a macro, but you can actually do it in the classical way. So you can actually create v-string as vec new, and then you can do the same process. So it's the vector just created another way. And using an iterator, a vector iterate. So we do a collection, we collect all these values up. So that creates like a number from like 0, 1, 2, 3, 4, 5. Define vector given capacity. You can predefine the capacity of a vector. And then you can see that you can get the length of it, and then you can get the capacity of it. So if you're building a program where you want a buffer, and then you want to monitor how much of it's used versus the capacity, then you actually have access to these parameters. And I made just a printout so you can see how it works. And then of course you can do these very simple for next. So you say for item in v capacity, then you can just print out each item out of normal. And then we get into this concept of slicing, and it's a reference to a part of an array or vector. Contains a reference to the where is it starting in the vector or the array, and then the length. So that's what it represents. And I must say that when you're reading Rust code, it's if you haven't been doing it for a while, then it's gonna be really confusing in the beginning to figure out is it, am I using a slice now? And do I need to use a slice? Or do I need to use the original object? So it's and then what functions take both original, like a vector and array as they are, and what require a slice. So it's not super intuitive. On the other hand, I think that when they designed Rust, they wanted to make it transparent, so you wouldn't, to a certain extent, you wouldn't need to think about it. But then the drawback is then for those poor people like me included, who haven't done years of Rust development, then it's not so intuitive in all cases to say, okay, now it's going to be a slice and now it's going to be a pure vector. But anyway, I made a simple example here, vector to slice and then array to slice. And so here we have a slice vector. Let's see what I thought I was going to do here. Yeah, exactly. So this is where it gets tricky, that this is actually pointing to the same data that we have created here, but this is a slice. But you don't see it. I mean, you don't see it anywhere that this is a slice. So that's why I tried. Yeah, you see how I got even confused about my own example. But the idea is that these are the pure entities, and then suddenly, when you do this assignment here, it's actually a slice now. It's not the original vector or array. But they're very useful. I mean, the slicing or the concept of slice is very useful in many different ways, and there are lots of examples how you can make it to mine data out of data sets in a very complicated way. But I didn't want to make too many complicated examples, scare everybody away. But my main message here is that when you're dealing with slices and vectors and arrays, it can get confusing in the beginning. And then, passing a slice when you may not notice it. So, So, like, you're looking at this code and then it's like, am I passing a slice or the vector or the array? What? So, for example, here you have the print function and it's a vector to slice and then slice arrays. Creating a specific slice to pass. This is so you have a slice and then you can actually say that, okay, I only want those elements passed. And then start from element 2 and to the end, or take only 1 to 3. So now we'll have a look at string types. There are 2 types of strings in Rust. And then I can't cover all the functions available for string because I'll just take too many. But let's look at some more interesting, or the basics. So string literal you can use escape characters here when you're building the string, and that most are the double quotes and then carriage return. But this is unique to Rust. You can do this kind of stuff. So long line spaces after new line included. Now this is actually, so it'll be A and then it'll be space B. So that's how it prints it out. But if you don't want that, if you want the second line to continue directly after A, then you use this character here. So that's a syntax that's not in another place. Also, you can say that, okay, you're fed up with doing this // to get backslash is in the right format for a file, like here in the file address. So then you say, okay, use a raw string, so then it doesn't care about the escape characters. And then if you want to get even more extreme, then you can say, okay, use raw text with this type of prefix, where you have R and then hash, 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 and then it ends here with double quotes and then hash, hash, hash. And then it absolutely doesn't care what you put in there. I tried to make a relatively complicated, so you'll actually notice it doesn't escape that, you know, and neither does it care about that either. And then you can define strings as bytes. So this is actually GET as a byte array, an ASCII character byte array. And then here it was like, tried to like, okay, we've assigned it, now we want to print it, but this won't work because it's not a print. It's not a string type, because print ln needs a string. So then you actually do have to convert it. So one of the many ways you can convert it is from UTF-8 to lossy, and then you just take that one, put it in there, and then it gets, you can convert it, and then you can print it. That was what I wanted to point out, that a string is in many ways considered a vector. Encoding is, however, variable length in Unicode, so many memory layouts is a complex issue. And then you have this concept here, which is address at str, which is actually a string slice. So the string slice in itself can't be modified. And as I was pointing out when we were talking about is it the original object or am I dealing with a slice? And then you have the same confusing thing with you know, am I using or do I need to use a string or a slice of it? Like, but anyway, I made some examples here. Convert into a string. So then you use this toString here. So if you actually do have a slice, which is this one here, and you want to convert it to a string, then you can use the toString. What else did I want? Or you can use the format as another way to convert. Let's see, or to get a string. And then we had some yeah, it was the, you can do, this was when you have vector elements, then you can actually concatenate them, or you can join them together with the delimiter. So that's just text formatting. And then using strings, there are many different, yeah, the usual stuff, like, you know, is it greater or less the, and then you have to read the documentation of explicitly what are the, you know, for example, how does that work, like specifically in the context of Rust. And then there's some special string-like types that are very useful to actually know about. So if you're dealing with operating system specific path types, then you actually do have a dedicated object and then a slice of. And then for operating system, you know, when you set operating system, like on Windows, when you use set and you have operating system value string pairs, then you actually can access the those raw values with OS string, and then the same here. And then and I forgot what this one was about. Can't remember. No, this was C-string. Yeah, this is that you actually do have access to C-string, the capability to handle C-string. Which is the idea that you have the characters and then it ends with a null. And I just wanted to mention that Rust kind of divides types into what's could be semi-considered built-in, even if one can argue that vector and other stuff, they're not even built-in types. But let's say that they, in most information that I've been reading up on, the ones that this stuff that I went through is considered like built-in types. And then you can add on to that with so-called user-defined types. And there are structs and enums and traits and functions and closures. However, arguably speaking, of course, when you're using Rust and the Rust standard libraries, then they all are kind of represented one way or the other, but they are considered user-defined. So we'll be coming back to that. So anyway, I hope you found that entertaining. A little bit useful. This is partially based on also hands-on experience of trying to understand how when I've been reading code and trying to make code, then a little bit of sometimes get stuck with these. What are the types that one can use, and all these things with the different parts. I found that this is also, I've been using this myself to remind myself what are the basic types, and what is the basic functionality related to the basic types. So it's made it faster for me to read code and also generate code. So anyway, just as a reminder, like I said in the beginning of the video, I'll load this up to my GitHub site. You can go get it totally free. I'm not taking any money for that. And see you in the next one.